So some good work here on our study of using derivatives and antiderivatives to relate rates of change together. We're going to be given the velocity of a particle in the graph below on an interval from 0 to 50 seconds, where time is measured in seconds and velocity is measured in meters per second. So I can kind of see this piecewise function shows the velocity of the particle. Velocity is increasing 0 to 10 seconds. Whatever this is, like a car or a particle or whatever, is speeding up. Then the velocity remains constant at 15 meters per second between 10 and 20 seconds. Speeding up again to a maximum velocity of 25 seconds between 0 and 30 seconds. And then for the rest, we're decelerating back to its resting point after 50 seconds as it decelerates down to its velocity of 50. What is the velocity of the particle at 10 and 30 seconds? At 10 seconds, what would you say? Read the graph. What's the velocity at that time point? Yes. And at 30, I want to say that's where its maximum velocity is at. Looking at the graph, right? On your handout, at 30 seconds, the velocity should be 5 meters per second. Easy, just reading the graph. It's asking about the velocity. We have the graph of the velocity. This isn't hard. For part B, what is the total distance traveled by the particle over the 50-second interval shown? Now it's not asking me about the velocity at 50 seconds. It's asking me about the total distance traveled by the particle over the course of 50 seconds. How could I use derivatives or antiderivatives to answer this question? Think about how we just did this on your warm-up. I've been given the velocity, and I want to find the total distance traveled. What did we use or approach with? Take a look. You bet. Antiderivative of v of t to dt from 0 to 50 seconds. Now that's pretty easy algebraically when you're given the expression, but we're just given the graph. Geometrically, what does that antiderivative refer to? So let's evaluate this definite integral by taking the area under the curve. I've got a couple different pieces I can kind of chunk this up into. Break it up into this right triangle here on the left, rectangle here in the middle. How can I break this up? Triangles in a rectangle, you're thinking? Got it? Yeah. Just kind of slice and dice. Find the areas of each of these pieces, and then the composite would just be the sum of all of them put together. For a triangle, its area would be half base times height. So 1/2 times 10 and 15. See, 10 times 15 is 150. Half of that makes 75. Got a couple of different rectangles. Don't these two rectangles have the same area? Yeah. As we've kind of sliced them up. So this rectangle has a base of 10 and a height of 15. 10 times 15 is 150, but I have that twice. A couple more right triangles left here. How about I do the big one to the right first? Half base times height, so 1/2 times the base of 30 to 50. 20 times the height of 25. Half of 20 is 10. 10 times 25 is 250. And the right triangle here at the top. Half base times height. The base is 10. The height is also 15, 20, that's 10 too, right? This is a length of 10. Half of 10 is 5. 5 times 10 is... As you're working through your own area calculations, do those look right because we kind of chunked it up? So let's add them all together. The total distance traveled on this 50-second interval. Let's see here. There's 300 and 300. 150 and 150 makes 300. 250 and 50 makes another 300. So 600 here plus 75 more. $675 meters. Distance is measured in units of length, meters. You're given a graph of a function. To evaluate the definite integral, it's just the area under the curve. No sweat. A couple more parts here. What is the average velocity of the particle in the 50 seconds shown? Average velocity. How can I set up a derivative or antiderivative to identify that quantity? Sure. Which should make sense. How do we define the average value of the function? As 1 over b minus a. That's the definite integral from a to b, f of x dx. Area under the curve divided by the length of the base to give you the average height of the function, average value of the function on the interval. So you're saying take the area under the curve, which we've now defined to be the total distance traveled, divided by the length of the base. How long it took to travel that for? How far is it from 0 to 50? What's 50 minus 0? Here's the definite integral. We accumulated the area for to find the total distance traveled. Divide that by 50. What do we show on there? 675 divided by 50. $2.5. So for average velocity, I think this is measured in meters per second. I think we're about halfway home here. We've got D and E. Now we're bringing in acceleration and relative speed. When is the particle speeding up or slowing down? On party. What is the acceleration of the particle at 15, 25, and 40 seconds? At 15 seconds, what would the acceleration of the particle be? How could I find that? how does acceleration relate to velocity? Let me ask you that. We have the graph of the velocity. We're talking about acceleration. So how are the two related? The acceleration is the rate of change in the velocity. So shouldn't the acceleration be the derivative of the velocity at that point? Well, we're not given a function to take the derivative of. So geometrically, how could I find or evaluate the derivative at 15 seconds? The slope of the graph, right? The slope of the tangent line, the slope of the curve at this point would be the value of the derivative. Or in context, the value of the acceleration at that point. What's the slope of the graph here? At 15 seconds, what's the slope of the graph? Since it's horizontal, don't let me catch you, it should be what? Here. 0 meters per second, or meters per second squared. Why would that make sense? Think about what's happening with the particle at that point in time. What's true of the velocity between 10 and 20 seconds? What's true of the velocity on that interval? Is the velocity changing between 10 and 20 seconds? No, because it's just a horizontal line, right? So the car or particle, whatever this is, can't be accelerating because the velocity is not changing. It's traveling at the same speed or velocity on this interval. So the acceleration in the particle is going to be 0. Now at 25 and 40 seconds, I no longer have any horizontal lines. I just can't look at that and say, all right, it's a flat line, 0 is the slope. Done. At 25, what do I have to do? How can I find the slope of the graph at this point in time? I can define slope as what divided by what? Yeah, just distance divided by time, speed divided by time. It's the slope of the graph here, change in y over change in x. How much this divided by how much this. Find the slope from point to point. 25 seconds is between 20 and 30 seconds. So take the change in y over the change in x, the change in the speed over the change in time for that line segment on the graph. 25 minus 15. Velocity changed by that much. In how much time? What's the change in delta t? Minus 20. (30 minus 20 is 10 seconds. 25 minus 15 is also 10 seconds. Meters per second. What's the acceleration? Meters per second per second. What's going to be true of the acceleration now? Down, it's decelerating. As its velocity comes to 0 at 50 seconds. So the acceleration should have what sign? Look at it. How can I find the acceleration at 40 seconds? How can I find the slope of the graph at this point in time? Well, very similarly, let's just find the slope of this line segment. Endpoint at 30 to endpoint at 50. Change in y over change in x. Change in the speed over the change in the time. So let's see here, change in the speed. 0 minus 25. Divided by the change in delta t, the change in the time. At 50 seconds, the velocity was 0. 30 seconds, the velocity was 25 meters per second. That's a total change in 50 seconds minus 30 seconds. Change in y over change in x, change in speed over change in time. So negative 25 meters per second over 20 meters, 20 seconds. What does that reduce down to? 25 out of 20. 5/4 or negative 1.25, negative 1/4. Negative 5/4 meters per second per second. Take a minute. Would you guys answer the last part? On what time intervals is the particle speeding up or slowing down? Explain why. In terms of rates of change, explain why. Well, they're working, guys. Those of you online, are you able to kind of follow along okay? Do I need to re-explain anything as they're working?
No,
I'm doing good.
Okay. Like I said, kind of our goal here is to do sort of similar questions that we did with antiderivatives and expressions for the velocity. We're just now given the graph of the function instead. I see two intervals where the particle is speeding up and one interval of time where it's speeding down. On what interval the particle is speeding up?
0 to 10 seconds.
0 to 10 and
20 to 30.
okay. Wow.
Because that's the point in the graph where
That's the part of the graph where
the line's going up.
slope is going up. So what's true of the velocity? on these intervals?
Velocity is positive.
Velocity is positive. Could a particle be speeding down if the velocity is positive? Could the particle be slowing down even though the velocity is positive? Sure. The acceleration would then be negative. What's true of the acceleration on these intervals? Velocity is positive here and here. I can see the velocity of these two line segments is positive. What's true of the acceleration for these two line segments? It's also positive because, like you said, the slope of the graph is going up, right? When velocity and acceleration have the same sign, strictly both positive, are both negative, an object is speeding up. Both A of t and B of t are positive. For a particle's speed to be increasing, velocity and acceleration have to have the same sign. If they're both positive, it's speeding up as it's going up. If they're both negative, it's speeding up as it's slowing down. Or falling down, or excuse me. Velocity and acceleration are both negative. It's speeding up as it's falling down. Where's the particle slowing down?
30
to 50 seconds. Why do we think there?
Slope is negative.
And slope represents what rate of change? Well, the v is just the whole graph itself. Velocity is given by the graph. The rate of change in the velocity, the slope of this graph, tells us the acceleration. So what's true of the acceleration between 30 and 50 seconds?
It's negative.
Negative, because the slope of the graph is going down. So if velocity is positive, since this graph is above the x-axis, and the acceleration is negative because the slope of the graph is going down and the line is decreasing from left to right, we're slowing down, right? Going from a larger velocity to a smaller velocity. Obviously, that means it's slowing down. B of t is positive. A of t is negative. Why don't we take the last 5 minutes of class and I'll let you guys get a jump start on what's on the back page here for a different time interval.